This is EL-Hadik from University of Louisville, and today we're gonna go about our presentation cognitive performance application. Our presentation is gonna be broken into those different sections, and we're gonna go in detail about each one right now. So Java application is widely adopted, and it's very well known for its web programming capabilities, and mainly for its multiple threading techniques that enable it to uh, uh, deal with multiple or concurrent requests from the users, and that's why it's very much used in many web applications, including e-commerce applications. In the e-commerce application, it's very heavily reliable or very heavily rely on the integration with the database, and the JVM use a database as a common resource, dynamic common resource. However, JVMs can be scaled, database cannot be scaled, and that could lead to bottleneck situations. Those bottleneck situations can lead to an immediate business loss in a world where the web application or the e-commerce application needs to be up and running 99% of the time. On the previous on a practical solution and the theoretical solution part, we noticed that most of the traditional or industrial solution revolve around query optimization, increasing memory, caching, and splitting the database. In the query optimization, sometimes it's hard to do due to the complex relationship in the database. Increasing memory could also require investment on the hardware specification. Caching and splitting the database, you run into problems of invalidating the cache or keeping the two databases in sync, and also it requires investment on the hardware specification. On the theoretical solution, pretty much it revolve around constituting a queuing engine to stream down the demand on the database, which we use some of those solution into and embedded into our solution to provide a comprehensive solution. Our solution pretty much revolve around this concept that we will build 3 layers as an extension to the JVM. Those 3 layers, the first one is the learning engine. The learning engine learns when the bottleneck happens and how to detect the parameters of the bottleneck or the performance parameters, so it can threshold the system performance and understand when the bottleneck happens. The analytic engine, it's more like an early alert mechanism, and it keep watching the demand and the relation and the different relation that could lead to a high demand on the system, such as shopping seasonality or weather conditions. And then the queuing engine is our rectifying mechanism that will stream down the request on the database when there is a high demand or when the threshold of the performance has been reached. The one thing to notice is that the queuing engine acts on the signal that comes from the analytic engine or the learning engine. This kind of enhanced signal, actually we quantify it to have benefit in reducing the number of the bottleneck situations that happens on the system. The uniqueness of this approach is pretty much it can be scaled to all other performance problems, not just the database, and it required less and less human interaction into the system, and it works well with a project that has low budgets. We took a snapshot of the system to understand the, the domain of the problem and uh, to capture the the parameters such as the CPU utilization and Java heap ratio and query response time. And we run it first with like simple queries that doesn't retrieve too much information from the database and so on, and so it wouldn't occupy a larger space on the Java heap. And this is just to see the relation between the CPU utilization and the number of threads competing for the CPU time at that time. And then we noticed that the higher the number of threads competing for the resources, the higher the CPU utilization percentage is, and the higher number of threads actually leads uh, to a higher response time. This particular thing led us to justify our rectifying methodology, which is first come first served queuing engine that will resolve on its own once the performance condition improves. And then we also run another test to understand the effect of having a higher Java heap size resulting from higher data size retrieved from the database. And we notice it's pretty much acting in the same way as in the previous experiment, and that could that could be due to the fact that our Java heap didn't occupy much space um, on our RAM, and that's why it didn't crash the system. That being said, our learning engine is based on a neural network, and we use the neural network because we could have multiple parameters leading to the bottleneck situation, and to avoid an interference of a domain expert to set the right weights on each of those parameters. We use the neural network to generalize the solution in case of ambiguity on which parameter has more significant toward more significant leading to the bottleneck. And we also we used a supervised mode for our neural network to deliver this to deliver this solution. For the analytic engine, we monitor different parameters also. In our experiment, we didn't use external factors such as the shopping seasonality, which is could be a room for future work. But for this particular experiment, we used the response time, and we number of SQL transaction, memory utilization, CPU usage, and number of JDBC connections to understand the relation between them and the bottleneck condition. We use different models, predictive models such as the linear regression models, the multilinear regression models, and polynomial regression models. And we run them at the same time, and based on the error percentage, we choose the best fit model among them and trigger the signal from the analytic engine based on that. The queuing engine, as I said, it's a Java-based native queuing engine, first come, first served, and it has a pass-through and queuing mode. Pass-through when there is no signal being triggered, a queuing mode when the signal is triggered from the analytic engine or the learning engine. And once a signal is triggered, a queue structure is being established to address all the JDBC database queries. And once again the signal of the performance being improved, we go back into the pass-through mode. And pretty much the concept is just to stream down the number of concurrent database queries into a queue structure, so we can stream down the demand on the database and avoid bottleneck situation. We run an experiment on the system with a number of with number of threads, without no performance enhancements, without adding any of our components, and we noticed that the system is crashing mostly at the 100% most of the time. And we collected those data statistics, including the minimum, the maximum, the standard deviation, and average and median. The average is what we were very much interested on. We noticed that it really improves. As you can see, it's not hitting the 100% after just adding the learning engine and the queuing engine. And we noticed that we could brought it down to the CPU utilization, the average CPU utilization, we could brought it down to 87%. After adding the analytic engine, we also noticed a good improvement there as well. And CPU utilization, the average CPU utilization came down to 84%. That's pretty much to our solution, and thank you very much for your time.